Alright, intro to exponential functions. An exponential function is a function that can be described by an equation of the form y equals a times b to the x, where b is greater than 0 and b cannot equal 1. So b has to be any number greater than 0 where it cannot equal 1. Where the a represents the y-intercept and the b is the exponential rate of change. Now we have two types of graphs. We have a growth or a decay. Now when we look at a growth, to have a growth, that b value has to be greater than 1. If b is any number greater than 1, the graph is going to grow because it's going to grow exponentially. And if the b value is less than or equal to 1, it's a decay. So if it's between 0 and 1, like 0.5, 0.25, 3/10, 1/3, they are decays. They are numbers that are between 0 and 1. So now the next thing says state a and b for the following exponential functions. Indicate if it's a growth or a decay. Well, a is our y-intercept, and that's the number out front. So a is 5. And then b is our number inside the parenthesis. So b is 2. And since b is greater than 1, this is a growth. So now we have a growth. Question number 2. Well, when it's in the form y equals a times b to the x, well, we have b to the x, which is 2 to the x. Well, this is really y equals 1 times 2 to the x. So that means the value of a is 1, the value of b is 2, and since the value of b is greater than 1, this is a growth. When we look at 3, we have y equals 100 times 0.5 to the x. So we have 100, which is our a value. 0.5 is our b value. And once again, b, 0.5, that's less than 1. So this number is between 0 and 1. So that means this is a decay. We're going to look at the difference between growths and decays in graphing. When we look at number 4, we have our a value, which is 0.25. The b value, which is 3. B is greater than 1. This is a growth. And number 5, once again, we can say that this is really y equals 1 times 0.5 to the x. So a is 1. B is 0.5. Since b is less than 1, this is a growth. It's between 0 and 1.5, between 0 and 1. And when we look at 6, y equals 3 to the x. Y equals 3 to the x, so this is going to be y equals 1 times 3 to the x. A is 1, b is 3, this is a growth. Now, if we flip this over, it says properties of exponential functions. Now, each exponential function has this thing called an asymptote. This is a keyword that we're going to need to know. An asymptote is a line that the graph continually approaches a given curve, but does not meet it at any finite distance. What this means is that the graph, when we start to graph these, you're going to notice it's going to get very close to this equation y equals 0, but it never gets there. So the number gets close to it, so it's going to be 1, then 0.5, then 0.25, then 0.075, and 0.0025, 0.000136, and 0.0000457. It's going to get very close to that value of y equals 0, but it's never actually going to get to that value of 0. So if we look at this first one, it says y equals 2 to the x. So we have y equals 2 to the x. And now we can actually look at some of our properties. So we can take our graphing calculator, go to y equals, and we type in 2. Now 2 to the x, we have to do that caret button, which is above the division sign. So now we get y equals 2 to the x, and we can look at our graph. So now if you notice this graph down here, it looks like it starts at like -3 or something, and then gets a little bit bigger, and then all of a sudden it's starting to shoot up. Well, once again, we have this asymptote at that line y equals 0, because this graph looks like it's going to gets to 0, but if we go to our table, well, if we notice, if we go up, as x is getting smaller, see how it's going 0.5, 0.25, 0.125, 0.06, this number is continually getting smaller. Now, this 9.8 e to the -4th, that means it's 0.00098. So it's going to get very, very small. to graph this, well, we can graph some of these points. Well, we know that 0, 1 is our y-intercept. So we have 0 and 1. And we can graph negative 1.5. So negative 1, it's going to be half of that, and then negative 2.25. So this graph's going to go down, and it's going to start curving. So it's close to this line, and now it starts to curve. And then as we keep going, then we get 1 and 2. So write 1 up 2. And if we continue with our graph, all right, so we get 2, 4, so write 2 up 4. And then we can do the last one, which is 3, 8. So write 3 up 8, and then the next value is going to be off the chart. It's going to be 4 and 16. So now we have a graph that looks like this. The way we can get these points, if we plug in 0 for x, 2 to the 0, anything to the 0 power is 1. 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16. So that's how we can also get the graph. So now when we look at our properties, well, the domain, well, this graph never stops going to the left, never stops going to the right. So the domain, all real numbers, or that fancy R. The range, the y values, well, this graph always is going up. Now, it looks like it never stops going left, but it never reaches the value of 0. So the range, y is always greater than 0. It's not equal to 0, it's always greater than 0. Now, compared to our quadratic functions, exponential are a lot easier because this graph never has a minimum, never has a maximum, never has a minimum. The x-intercept never crosses the x-axis. The y-intercept, we know that the y-intercept is 1, doesn't have an axis of symmetry. And then when we look at it, increasing interval or decreasing, well, we know that this graph is always increasing, so it's always increasing over the interval of all real numbers. It's never decreasing. Is it a growth or a decay? Well, the b value is greater than 1, and if you notice this graph, it's going up. So the graph is going up, so it's a growth. So this graph is a growth. And then it has this asymptote at y equals 0. That's the line that it's getting very close to. So this asymptote graph gets very, very close to this line, but never actually touches that graph of y equals 0. Then when we look at the next one, this one we have 4 times 1/2 to the x. Well, if we go to y equals, we type in 4 times 1/2. Make sure you put that 1/2 in parentheses. Caret button to the x, so we raise it to the power of x. And if we look at our graph, now when we look at this graph's coming down, so it's a decay, and because that value of 1/2, we can look at our table. So we can say, well, negative 2/16 off the chart. We can graph negative 1/8. So left 1, up 8. Then we can graph 0, 4. And we can graph 1, 2. Right 1, up 2. We can graph 2, 1. Right 2, up 1. We can graph 3.5. So right 3, up 1/2. 4 and 0.25. And then 5 and 1.25. And if we notice this graph is getting close to 0, so this time it comes down, and it looks like it makes a straight line there. It's approaching 0. So now we have our graph. Once again, we can look at these properties. Well, the domain never stops going left, never stops going right. So the domain, all real numbers. The range, well, the y values, this graph is always going up. So the range, it never hits 0, so the lowest value, y is greater than 0. There's no maximum, there's no minimum, there's no x-intercepts. The the y-intercept, it crosses the y-axis at the point of 4. So the y-intercept is 4. There's no axis of symmetry. Now if we look at this, is our graph increasing or decreasing? Well, the graph is decreasing, so since it's decreasing, it's always decreasing. There's no increasing interval, so it's decreasing for all real numbers. And is it a growth or a decay? Well, it's decreasing, it's a decay. It's also the b value is between 0 and 1. And our asymptote, this line gets very close to y equals 0, but it never actually touches it, it never crosses it. And they are some of the properties of exponential functions, labeling a and labeling b.